Welcome back for another wonderful lecture in Math 1325. We were talking about limits, so let's kind of finish this section 10.1 and look at some other information on limits. So remember, as a reminder, a limit describes the behavior of a function f of x when x is close, very close to a particular value of c. So this states that for any polynomial, which we talked about last time, how do you find the limit? You just simply plug in the value. You just evaluate the polynomial. We talked about one-sided limits versus limits in general. So the limit of f of x as x approaches c equals L implies coming from the left, coming from the right are equal. So let's look at an example, find the limit. What happens if you just plug in 2? Not a good thing, right? Because we don't really care the denominator. I mean, that could be 0 because then you'd end up with 0, right? But I think I said the denominator. I don't know what I said. But the numerator, we don't really care about. The denominator, that's when bad things happen. So last lecture said just plug in the value. Well, what if you can't just plug in the value because you can't divide by 0 in this case? Well, what about factoring? Do you remember that? Like a bad dream, right? Algebra, how to factor this? That's the difference of two squares. X is squared and 4 is 2 squared. So you could factor that into x minus 2 and x plus 2 and then cancel out x minus 2. And now it's okay to simply plug in 2 for x. And I get this limit of 4. So let's understand what this means. Okay, so I wanted to know this function. This is a rational function. As x is approaching 2, what's happening? Well, when I cancel this, you can see this is linear. If I graph it, it's just a line. The big thing, though, is x cannot equal 2. So we put a little hole there because if x equals 2, then we are actually dividing by 0. But notice, if I get really close to 2 from the left-hand side and the right-hand side, the value of the function is getting close to 4. And that's where I keep saying over and over, a limit could care less the value of the function, because in this case, at x equals 2, there is no value of the function. But the limit as x is approaching 2, that's where we get this 4. All right, so let's look at what's called indeterminate forms. So it is important to note that there are restrictions on some of the limit properties. So for example, our rational, okay, if we have this limit with our rational and we get a 0, then we might have some kind of issue going on. Like for example here, I can't just plug in 0 into the top and the bottom, because what happens, I end up getting 0 over 0, and this is what's called to be indeterminate. So indeterminate is used because the limit may or may not exist. So the first thing we have to do is figure out, do we have something in indeterminate form? Where that would be where you end up with 0 over 0. Well, our last example, that's what happened. If I just straight plugged in 2, I end up with 0 over 0, and this is in indeterminate form. So what I have to do is see, is there something else I can do? Can I factor this? Is there another step? We're going to see some other little tricks to get this out of this indeterminate form to be able to take a limit. So find this limit if it exists. Is this an indeterminate? I don't think so, because if I plug in 1, I don't get 0 over 0. And as I mentioned before, we could care less about the numerator, because if it's 0, then that just means our answer is 0. Get where you graph these, because if you graph them, it makes sense what you're doing. I want to know this function, which is this purple line. As I'm approaching 1, what is the value of my function approaching? And as you can see, it's approaching 0. How How about this one? What happens if I plug in 1? I get my 0 over 0. So what you do next is you look to see if you can factor, which that bottom is the difference between squares. That's x squared minus 1 squared. I can factor x squared minus 1 into x plus 1 and x minus 1. I can cancel, so I end up with a 1 on the top, because that's x minus 1 over x minus 1 is just 1. And now I can actually plug in 1 on the bottom, and I get 1/2. What did I say to do? Graph these. So if I graph this, and as x is approaching 1 from the left and the right, I can't just plug in 1. That value does not exist. But as I'm approaching it, it appears that the value of the function is approaching 0.5 or 1/2. All right, let's look at this one. What if I plug in a 1? Is this an indeterminate? No, because the numerator's not 0. So what's the answer? Does not exist. So this is where we talked about when the denominator is 0 doesn't always mean that you're going to end up with an indeterminate, because the numerator would have to be 0. So this means the limit does not exist. And if we look at this on a graph, as x is approaching 1, what I can see here is if I'm approaching it from the right, that function's heading off to infinity. If I approach it from the left, that function's heading off to negative infinity. And so if you remember, these were called asymptotes, and so in this case the limit would not exist. Let's look at an application of limits. Assume the volume discount in the table below apply to an entire purchase. So in other words, the volume, if you're between 300 and 1,000, 3%, 1,000 and 3,000, 5%, and so on. If X is the volume of a purchase before the discount is applied, then write a piecewise definition. So remember, a piecewise is you have one piece, which is one function, then a next one, and so on. So I'm going to take this information from the table, and I'm going to create a function called d of x, and I'm going to write it piecewise. That says if I'm at x is between 0 and 300. Well, if you notice here, if I'm greater than or equal to 300, that's when my first discount applies. Well, what if I'm from 0 to 1 to 2 to 3 all the way up till I get kind of close to 300, but I can't touch 300? You don't get a stinking discount, so you just pay whatever the X is. Well, and then you can see my discount amounts. What I did is I took like the 0.97, because that's 100% minus 3% would be 97%, and changed it to a decimal. 0.95 for 5%, 0.93, and all I did was just simply match this information. So what I could do with this is I could use this to investigate the limit of d of x as x approaches 1,000. So as I'm getting close to 1,000, what's this discount? Okay, now what? Well, remember how we find one way a limit is find the left-hand side, find the right-hand side, and see if they're equal. So the left-hand side limit. Well, what the heck is it? Left hand of what, right? What's the left of 1,000? So I would be in this second row here because I'm getting really close to 1,000, but I'm not at it. So I would be at the 0.97 times 1,000, which would be 970. Well, what if I'm coming from the right-hand side, which means I'm above 1,000? Then that would be this line, the 0.95x. So again, what's the limit as x approaches 1,000? You remember, it does not exist because the left-hand side does not equal the right-hand side. All right, remember we talked about this difference quotient, and I said this is very important. So all of this difference quotient is a slope, right? Because this is the change in the y over the change in the x. What if I wanted to investigate this limit as h goes to 0? As you can see, you certainly cannot plug in 0, because if the limit as h approaches 0 of the numerator equals 0, then I have something in indeterminate form. So let's find the following limit for this function using the difference quotient. So the first thing I do is I write my formula. Now what I'm going to do is these a's are for a particular x value. In this case are going to be 3's. So I plug in 3. And then I evaluate my function at 3 plus h and at 3. So I have 4x minus 5. Where you see an x, plug in 3 plus h, minus 5. And then minus, be careful because you want to be sure and distribute this negative sign, 4x, where x is 3, minus 5, all over h. Notice this is in indeterminate form, because if you look here, you're going to see 4 times 3 is 12, minus 12. I'm going to end up with a 5 and a negative 5. Those are going to cancel. So you're going to end up with 0 over 0. So let's play around with this a little bit. Let's go ahead and distribute some things out. And as you can see here, I'm just simply 12 minus 5 is 7. 12 minus 5 is 7 there. My 7's cancel. And I end up with this limit as h approaches 0 of 4h over h. Well, I can cancel the h's. And what's the limit of a constant? Remember, last lecture, if I want to find the limit of a constant, I don't care what h is approaching. It's a constant. I just get that constant back. More to follow about this. But the big key here is we started by using a table to investigate the idea of a limit. Remember, as we got really close to 2, so that's more of an intuitive way. Then we saw that if the left and right hand limits at a point were the same, then the limit existed at that point. We saw different properties. You can add, subtract, multiply, divide, bring out constants for limits. And so now we are ready to go full blast with our calculus.